All right, so we're going to do the same thing we do every week. So we're going to first recap what we learned in week 3, and then we're going to forecast what we're going to learn this week in week 4. All right. So the first thing we did last week was learn a learning algorithm called naive Bayes. All right, this is a Bayesian approach which has the idea of using a naive assumption that the individual features are uncorrelated in our X vector. Right, they independently predict the outcome variable Y. Right? And the second part of the name is, of course, Bayes, right? So Bayes means Thomas Bayes or Bayes rule, which means we're going to calculate this posterior probability by using the likelihood timesing by the prior, right? So it gets divided by the marginal, but we don't need to worry about that because the data is actually given to us. We don't get to decide how likely it is a particular data instance is provided to us. It just is, either through the training data or when we're giving a data instance for inference, we don't get to decide what it is, right? We saw that we also often in the post lecture need to cater for smoothing when we don't have enough data, that we might want to add artificial instances to make it easier for us. Secondly, we went over nearest neighbor, or NN, right? Here it means nearest neighbor, not neural networks, that you'll see later. And we saw we could generalize this to use K of them, right? So this is a hyperparameter that we can tune as we wish. Okay. We saw that it's basically an instance-based non-parametric algorithm. Non-parametric meaning it doesn't have this theta, right? It doesn't have a particular idea of what parameters that we're going to have. Just memorizes the training data, and it votes for the nearest neighbor. And in order to do that, it needs a similarity function, right? Some way of calculating whether two instances are close by to each other. We also covered some very important concepts for later on in the course, which is importantly the idea of a cost or loss function. These two terms are synonymous with each other, right? So a cost function just lets us know how good we are doing on the actual training data, and that measures our performance. And hopefully, if the training and the testing instances follow the same distribution, this means that we're going to get good performance on the testing data, which is what we really care about when we do well on our training data. So we're going to optimize, try to set our parameters in such a way that we do well on the training data. Okay, so we also looked, now we're going to look forward in week 4 and think about the learning outcomes for this week. So this week is a pretty heavy lecture, I'm sorry, but we're going to cover all sorts of linear algorithms. And linear algorithms are basically the basis, the building blocks for anything more sophisticated. So it pays a lot of useful work to understand them very well. So we're going to describe the basic idea of linear classification and then move on to linear and logistic regression, right? Regression just means having a real valued output. We're going to investigate linear classification through this idea of the perceptron learning algorithm, or PLA, and we're going to look in the post-lecture about how to understand the mathematical proof of it. Some other important concepts that you're going to see this week are about gradient descent and the stochastic version of that, which are going to help us along optimizing our features and understanding bias and variance that we've already highlighted from our guest lecture. Finally, we're going to cover nonlinear mappings at the beginning of our post lecture, which will allow us to use linear algorithms for a whole slew of different problems, even if the original problem is not linear.